Hello, my name is Nelson Goosman, and this is my presentation for my research on apple fruit surface temperature prediction using weather data-driven machine learning models. For this research, I worked under Dr. Lav Coate at Washington State University's Research Lab in Prosser, Washington. Research motivation. Prolonged periods of elevated temperatures cause heat stress in maturing apples, leading to death of epidermal and subdermal cells. These conditions are referred to as sunburn. Heat stress leads to several fruit disorders in apples, reducing their marketability and decreasing yield at harvest. Fruit surface temperature is a direct indicator of heat stress. After the air temperature reaches 95 degrees Fahrenheit, apples are at risk. However, this is also dependent on other weather factors. From the example images of sunburn effects, we can see that having predictive measures of fruit surface temperature can be a crucial asset for growers. Heat stress mitigation techniques. Some common techniques that are used to reduce FST are overhead sprinklers that spray water directly on fruit, foggers that cool the ambient air temperature, overhead nets that decrease solar radiation, and a combination of fogging and netting. Overhead sprinklers can increase soil moisture and cause water core and bitter pit. Foggers have a high water demand, and netting can reduce the coloring of fruit. Accurately deploying these methods based on FST data can be crucial in reducing these downsides. It is important to measure FST so growers can improve the accuracy of heat stress management techniques and reduce their negative effects such as water usage, which is both environmentally and economically friendly. Research goals. Pertinent to this, the goal of our research is to evaluate the performance of a machine learning-based methods of FST estimation that are simple, accurate, and easily deployable. Current methods include direct measurement with a thermal probe, thermal RGB imaging, and energy balance models. Each of these models have drawbacks, which our method will attempt to solve. Data collection. In the orchard, there were 5 sections that we collected data from, containing various heat stress mitigation techniques, fogging, netting, fogging and netting, and sprinklers, as well as a control section with nothing. Each section contained its own weather node, collecting localized weather data and measured in-canopy air temperature, wind speed, dew point, and above canopy solar radiation. Additionally, fruit size data was collected using calipers, and surface temperature was collected using a thermal probe. During the 5 hottest days between July 12th and 29th, 2022, data was collected by hand. For each of the heat stress mitigation techniques, 3 apples directly exposed to sunlight were selected per tree for 6 trees total in 30-minute intervals. Here we see the in-orchard weather node in A, the thermal probe in B, and the open field weather station in C, which we trained a model on to determine the accuracy of open field weather data compared to in-field weather data. Additionally, the data used in the study was collected near Prosser, Washington in a private orchard. Model development. In our study, we tested 2 different machine learning algorithms, multilinear regression and long short-term memory. Multilinear regression is a machine learning algorithm used for predicting continuous target variables based on multiple independent features and works well for data with a strong linear correlation. It determines a linear relationship between the target and the features, which in this case is the weather and fruit size data and fruit surface temperature. A long short-term memory network is designed to process and make predictions on time series data. Unlike traditional neural networks, LSTMs contain memory cells that allow them to retain information for long periods, making them capable of capturing long-range relationships and time sequences. These memory cells consist of gates that control the flow of information, enabling the network to learn when to remember, forget, or update information as it processes the input sequence. LSTM network architecture. For the input layer, the model is given fruit size, air temperature, above canopy solar radiation, wind speed, dew point, time of day as a fraction of 24 hours, and day of year as a fraction of 365 days as independent variables. Layer 1 and 2 are LSTM layers containing memory cells. A dropout is applied to the first layer with a probability of 30% before it is fed into the second layer, meaning that 30% of the data will randomly be zeroed out on each pass of the training, which helps decrease overfitting. Layers 3 through 4 are standard linear layers that take the output of the second LSTM layer and compress it before a final FST prediction is output. Linear model architecture. For the input layer, we use the same data as the LSTM model. Layers 1 through 2 are standard fully connected linear layers feeding into a single output FST prediction layer. Results. Here, results from different model configurations are compared with the existing energy balance method of FST estimation. Results are compared using different data sources, in orchard versus open field, and with or without the use of fruit size. The best results come from a multilinear regression model trained using in-orchard data with fruit size, with a root mean squared error of 2.12 degrees Celsius across 3 trials. This model was more accurate than the LSTM model, possibly because of inconsistent time series data. Finally, we can see that it vastly outperformed the energy balance model, which had a root mean squared error of 15.37 degrees on our same dataset. From the absolute error histograms, we can see that the MLR model has a high frequency of accurate predictions with some outliers that bring the error rates up. This is a large improvement from the energy balance model. In reference to the MLR estimation accuracy, it was able to predict fruit surface temperature within 1.8 degrees Celsius for 88% of our 171-point validation dataset. In this graph, we see that the model fits most of the data, but has trouble estimating large or small temperatures. This suggests that we need more data to further train the model to predict a wider range of temperatures. Conclusion. This study highlights the use case of machine learning models in FST prediction using real-time weather data from open and in-field weather stations and associated data collected by growers or regional networks. Overall, a higher degree of accuracy can be obtained using multilinear regression model on in-orchard data, which performed better than the existing energy balance methods of FST prediction, as well as a long short-term memory model approach. The multilinear regression model was able to predict fruit surface temperature with a root mean squared error below 1.8 degrees Celsius for 88% of the validation dataset. These models only need weather and fruit size as input parameters, providing greater ease of use by the growers as a practical method of FST prediction. The energy balance root mean squared error averaged at 15.37 degrees Celsius, while the multilinear regression models average root mean squared error was 2.12 degrees Celsius. Overall, this study showcases a potential for FST prediction with commonly available weather data from either in-orchard or open field data as a possible solution for real-time fruit surface temperature prediction. Finally, I would like to thank Dr. Lavcoat, Basavaraj Amogi, and the Ag Aid Institute for their continuous support and mentorship throughout my internship.